1270 is already quite large enough.
So there are some different works going on, and in the end, of course, it's all a question how to quantify the errors. And that's because that's the main challenge in this field. Yeah. And then you want to stay as model independent as you can, but definitely, yeah, that's one way to go, and there's some works already being done in this. But you had more questions.
Okay. My impression is that you have converted the theoretical problem to experimental problem again. Okay, so and you stated the goal clearly, how accurate the data should be in order to reach the goal, say reduce the serial uncertainty by half to half. Now, okay, now what's the time you expect, or how long you expect we can reach this
time frame? Yeah. So yeah, to answer that question, yeah, we had a workshop, of experts in April, and the time frame basically is set by the time frame of experiment, because experiment will do this in 2000. Most of the data taking will take place in 2017, and it looks really, from the technical point of view, they're completely on time. Also from the funding, okay, in the US it's a very complicated funding situation, but also because they got this very high priority, also from funding, it looks to be on time. So this will be done in 2017, basically. So then, and these are the same people who have done the Brookhaven experiment, so the analysis procedure, everything, is basically very similar, and they're, experts in this. So one can expect results 2018. So that's basically 3 to 4 years, that's the time frame, sort of a PhD basically. So yeah, it's a good PhD subject.
Yeah, just make a comment. Actually, in the J-Park, there is also experimental proposal for measuring the G-2 for muon using some kind of astro code. They try to get in using some atomic physics technology to reduce the transverse.
Right.
I guess you're probably aware.
I'm aware of this. Yeah, I just didn't put it here now on the slides, but so these experiments use a different technique though. So it has the ultimate goal. It will be very interesting. There will be 2 measurements. I think there will be a little bit later, so there will not. But the Fermilab experiment is really the precession of muons in this magnet. So this is a technique which has been well studied and has given the results, most precise results up to now. So the J-Park technique, they do this for magical, I need to think, so magical frequencies where the electric field, there's always an electrical field component which vanishes. Whereas in the J-Park experiment, they don't do this, but they do it at lower energies. So there are 2 terms actually contribute. You need to disentangle. One term only is proportional to the anomalous magnetic moment. So it's a complementary technique, I would say. But indeed,
the sensitivity? I
yes.
cannot get a number.
What they are claiming, so there was actually also a talk by one of these representatives at this workshop, which you just mentioned. But the aim is also to have the same roughly precision, factor 4 improvement, but it's a new technique, so it means you need to study probably systematic uncertainty and so on. But it's roughly the same precision. Yeah, thanks for bringing it up. Yeah, I forgot to say that.
More questions?
With T-Latch.
Okay. I have a question. Then you just show the Q1, Q2, and then the 4 basically 4 area. So because if both are low, then you have the some. If you feel very both are high, you have the better capacity. So you basically apply this dispersion relation for one is small q, one is large q. But of course you probably can check out whether that's double counting or not. But what's the cut between the soft and high? Is it 1 GeV?
Yeah. So okay, it's a good question. So you don't want to double count things, right? So now if you have a dispersion approach, you can always set you have an integral, a double integral. So you can always say you integrate up to a given energy range, and you use one, let's say, technique in that energy range, and then you can use duality, let's say, above some, let's say, up to 3 GeV, and then from 3 GeV, you're using like duality argument, you're using perturbative approach in the other energy range. So, and then you match it. So, so you can, but in principle it shouldn't depend where you do it precise.
Sure.
So you can.
And Python, it definitely depends. So you got to, and finally you have to.
If you have a model, yeah, it's very difficult. If you start to add contributions, you don't know, because when you start to mix hadron and quark degrees of freedom, you will for sure double count things. But if you have a dispersive approach, you can always set your energy cuts and then do in one energy range one approach, and another energy range another approach.
For the one meson diagram, the distribution is finite.
It's all finite, yes.
And have you included the width of the meson?
The width of the meson. So you mean the hadronic width here?
Yeah.
So yeah, of course these states. So pion here is only electromagnetic decay. So it's only electromagnetic width which is entering there. But for instance, if you have this F2, which I've shown you, so this goes into a 2 pion state. So there indeed you need the spectral function. So it means you have a finite energy distribution. You can do this. So the tables which I've shown you for the sum rule was using the values from particle data book, which basically make Breit-Wigner fits. So yeah, this would be the simplest approach. Now for many states this is appropriate. There are states though like sigma meson, which can also couple to 2 photons, where you cannot do that. And then, of course, in sigma meson, F2 meson are anyway not the states you see in your detector. What you see in the detector is pi plus, pi minus, or eta and so on, or kaons and such states. So what really enters as an observer is the amplitudes or cross-sections of 2 photons into 2 pions. So ultimately, you shouldn't depend on what you plug in. I mean, just for the example, to show these sum rules, I projected them on these meson states because that's the way they're usually shown in particle data book. But if you do a dispersive input, what you need is are really the transitions of 2 photons to. So pion you can plug in because it doesn't decay strongly, but everything which decays strongly, you should put in the decay channel, like 2 pion state or 3 pion state if it's necessary. So that's the way to do it.
If there's no more questions, thanks, Marc. And,